We're going to start talking about acids and bases, and so let's define our terms. If you've worked with acids and bases before, you probably think of acids as H+ and bases as OH-. That is a pretty limited definition, and so we need to expand that a little bit. The most expansive and in a lot of ways the most useful definitions of acids and bases come from Lewis. When we talk about Lewis acids and bases, what we're talking about is the electron flow. So in a Lewis acid, we are accepting electrons, and in a Lewis base, we're donating electrons. Okay, so it's not about the H+ anymore. It's about where the electrons are going, which, for those of you continuing on to organic chemistry, that's the whole ball game, thinking about where the electrons are going. Okay, and as we get into organic chemistry, for some of you, we'll start to use words like electrophile and nucleophile in place of these. But again, we're not going to really use electrophile and nucleophile in this class. We'll stick with thinking about acids and bases. Okay, so as an example, BF3 is a really good Lewis acid because it's electron poor. Notice if I count valence electrons, 115 style, I've got 2, 4, 6. I don't have an octet. And so generally speaking, Lewis acids very often don't have full octets like that. And then something with a lone pair of electrons can act as an electron donor. Okay, and so we kind of say, like, okay, we think about this lone pair going and making a new bond to that boron. In this case, what we end up with is a new compound that's the product of the reaction of the Lewis acid and the Lewis base that has kind of this permanent dipole where I have a B- and an O+ like that. Again, we don't need to learn kind of how this reaction works or what anything is called here. This is an example of a Lewis acid and a Lewis base. Electron acceptor, electron donor. How do I know if something is Lewis acid? Again, it's probably something that's electron poor. The most common Lewis acids are boron and aluminum, and anything in that column, that third column of the periodic table, so I guess it's gallium and indium under that. But boron and aluminum, generally speaking, take 3 bonds and are short an octet. So anything that's short an octet, I'm thinking Lewis acid. This X here is a halogen, so it could be F, Cl, Bri, something like that. So BF3 is the one we talked about earlier. That's a good Lewis acid. We can also see transition metal halides, so particularly iron, cobalt, titanium, that kind of stuff, typically top row stuff. But if you see in chloride or fluorides or bromides, again, that's a good sign that you're thinking about Lewis acids, electron acceptors. Lewis bases, it's a little bit easier. All we're really looking for is, does it have a lone pair? If it has a lone pair, it can use that lone pair to go make a bond, right? 3 dimensions, make a bond. Okay, so again, Lewis acids, electron acceptors, often boron and aluminum, sometimes metal salts. Lewis bases, stuff with a lone pair. The 2 useful models, to my mind, for acid-base stuff is Lewis and Bronsted-Lowry. I don't know how to pronounce the cool line through the O. If you can explain it to me, I would very much appreciate that. Again, Lewis acids are thinking about electrons, electron acceptor, electron donor. Bronsted-Lowry, we are thinking about protons, H+. So we wouldn't call this a hydrogen atom because a hydrogen atom has an electron and a proton doesn't. Okay, so here, acid proton donor, base proton acceptor. There's also this Arrhenius base and acid thing. I don't think that's useful. We're not going to talk about it. So here, I want to emphasize that you need a proton. So when we talked about BF3 before, BF3 is a great Lewis acid, but it can't be a Bronsted acid because there's no H, right? It doesn't have a proton to give up. In a lot of ways, the Bronsted-Lowry acids and bases are subsets of the Lewis acids, which is to say any Bronsted-Lowry acid is by definition also a Lewis acid, right? H+ is a pretty good electron acceptor, so H+ could be considered a Lewis acid. So again, Lewis acid, more broad, Bronsted-Lowry, more specific, but we're also going to spend a lot more of our time talking about Bronsted-Lowry acids and bases in this class. So let's talk about strong acids very briefly to finish off this video. So in the Bronsted-Lowry sense, this is our acid equilibrium where I'm giving up a proton to water to get A-. Some acids will give up all of its proton. Then we call it a strong acid. Full dissociation, all of it is going to this. So if I dump any of these acids in water, I essentially don't have any HA left anymore. It is all this. So do you have to memorize this? It's a very short list, and yes. So here we go. Your hydrogen halides, HCl, HBr, HI. So hydrochloric acid, hydrobromic acid, hydriodic acid. You don't need to memorize the names. The formulas are fine. So again, these are your halides. They are on the right side of the periodic table. Notice that fluorine is not here. HF is a pretty strong acid, but it's not a strong acid. It does not fully dissociate. It doesn't belong in the list. If you oxidize these, so if a bunch of oxygen atoms end up binding to these halogens, you can get these perchlorate, bromate, periodic acid. You won't see those very much, but I put them here for completeness. They are strong acids. Finally, the two strong acids that you'll probably work with the most are nitric and sulfuric acid, HNO3, H2SO4. Again, highly oxidized, lots of oxygen atoms, kind of like perchloric and so forth. So this is your list. These are the strong Bronsted acids that will fully give up a proton. Anything else, any other acid is not a strong acid and will not fully dissociate. The one thing I want to end this video with is to say that acidity and basicity are not related. If something is a good acid, I don't really know about how good a base it is, and vice versa. So for instance, amino acids like this are generally pretty good at both. This nitrogen is pretty basic, this oxygen is pretty acidic. Okay? And so this is an example of something that could be considered both an acid and base, and yes, most of the time it's going to protonate itself and kind of work like that. Water is kind of okay at both. It's certainly not a strong acid, certainly not a strong base, but in different situations it can play both of those roles. Something like CH4, methane, natural gas, is terrible at both. It's a terrible base because I can't fit any electrons on it, and it's a terrible acid because it's really, really hard to break that CH bond. Okay, so is it technically a Bronsted-Lowry acid? Yes, it's technically a Bronsted-Lowry acid, but it's the worst, the weakest that there is. Okay, so again, kind of drill this into your head. If I know that something is an acid, that doesn't necessarily mean it's not a base. If I know something is not an acid, I don't know that it's not a base, or I don't know that it is a base, or whatever. They are not connected. To summarize what we've talked about in this video, the most general definition for acids and bases comes from Lewis. Lewis acids, electron acceptors. Lewis bases, electron donors. When I'm recognizing a Lewis acid, I'm looking for boron and aluminum because they're usually short an octet, or I'm looking for some kind of transition metal salts, often from the top row of that middle part of the periodic table: titanium, iron, cobalt, nickel. When I'm looking at Bronsted-Lowry acids and bases, those are a more specific, a subset of the Lewis case. Bronsted-Lowry acids, proton donors. Bronsted-Lowry bases, proton acceptors. The strong Bronsted-Lowry acids that you should commit to memory are what we call HX, so HCl, HBr, HI. The oxidized versions thereof, where there's 3 or 4 oxygens kind of tacked on to that halogen atom. And then the two other big ones are nitric and sulfuric. Very, very strong acids. We'll have to be careful to use them, but they are very useful, so we will use them.